Hey everybody, this is Mr. Lowry, and this is Simplifying Radical Expressions Part 3. If you missed class on November 2nd for A Day or November 3rd for B Day, then this will help you get started with your homework. In this activity that we're going to be practicing simplifying radical expressions again, but we're going to be dealing mostly with division type problems. The first thing we need to know here is a property of radicals. And that property of radicals looks kind of like this. If I have a root, and n stands for the index of the root, if I have the root of something, and I'm dividing that by the same index root of another value, I can rewrite this as one big root with a over b inside the root. So the index has to match. This has to be the same kind of root, both square roots or both third roots or whatever. And if that's the case, then I can write one root with that quotient a over b inside. That's going to help us simplify some of these. If you take a look at number 1, for example, you see that there's a square root of 15 and there's a square root of 80. So what we could do, one of the things that we could try first, is we could just rewrite this as the square root of 15 over 80, because we know that 80 and 15 both have a common factor of 5, because 80 ends in 0 and 15 ends in 5. So we know there's probably going to be a common factor there. When we divide out that common factor of 5, we're going to get the square root of 3 over 16. In other words, I'm just simplifying 15 over 80 to 3 over 16. So I took the two roots, because these are both the same index number, right? They're index 2. Put them in the same root, simplify the fraction. Now I could do the opposite, and I can break them up again. So this is square root of 3 over square root of 16. The advantage of doing that is square root of 16 I know is 4. So when all is said and done here, I got square root of 3 over 4. All right, and there you go. So this strategy of putting two roots together, breaking the two roots apart, kind of going back and forth, is a way that you can manipulate your expressions to simplify things, cancel out common factors, or take roots. Now let's look at another one that has a higher index here. So these are both root 3. That's okay. So I'm going to write one big root 3, but I'm going to put a 15 over 40. Now 5 goes into both of those things, so I'm going to have the third root of 3 over 8. So kind of similar to the last problem we did. Now from here, what I might want to do is write the third root of 3 over the third root of 8. So now I'm going backwards with that same property. Take two different roots and put them together, simplify, and take that one root and split it into two roots. The reason why is the third root of 8 comes out nicely. 8 is a perfect cube. So I have the third root of 3 on top, which I can't really do anything with. But the third root of 8 is actually just 2. Okay? So that's kind of how that one works. All right, let's look at one more. Let's look at number 7. Okay, so in number 7, I can write this as the fourth root of 6 over 32. All right, now I know that those are both even, so 2 goes into both of them. So this is going to be the fourth root of 3 over 16. Okay, now 16 is 4 squared, but it's also 2 to the 4th. So when I rewrite this, fourth root of 3 over the fourth root of 16, right? The fourth root of 16 comes out as a 2. So this is the fourth root of 3 over 2. So all those problems we did are kind of similar in that they, end up with a root 3, but this one's a square root of 3, this one's a third root of 3, this one's a fourth root of 3, and depending on what we have, a third root of 8 we can take, fourth root of 16 we can take, a square root of 16 we can take. So that's one strategy that you can use to simplify your radical expressions. All right, in the next section, we have to talk about a new phrase. Okay, so this new phrase is rationalize the denominator. So an expression isn't fully simplified until there's no roots in the denominator. So although this looks pretty nice, the fact that there's a root down here means that this isn't fully simplified. Okay, so what rationalize the denominator means is get rid of any of the roots in the denominators. Your final answer should never have a radical in the bottom. Okay, so these all have radicals in the bottom. We're going to have to take care of that. If you think about it, the square root of 3 is an irrational number. What we want to do is we want to change that irrational number to a rational number. That's what rationalize the denominator means. It means make that denominator from an irrational to a rational. Okay, in order to do that, we need to talk about a property that we've talked about before, but we just need to revisit it. So off to the side, I'm just going to give you kind of some ideas here. If I have 2/3 plus 4/5, and I want to add those two fractions, what I'm going to need to do is I'm going to need to change the denominators so that I have common denominators. The way I do that is I multiply by a form of 1. So if you think about it, 3/3, the reason why I'm allowed to multiply by 3/3 is because that's just 1. I can multiply by 5/5 as well because that's just 1. So I'm not changing the value of these fractions, I'm just changing what they look like. 5 times 2 is 10 and 5 times 3 is 15, but 10/15 is the same as 2/3. Those are equivalent. We call those equivalent fractions. Over here on this fraction, I have 4 times 3, which is 12, over 5 times 3, which is 15. Again, 4/5 and 12/15 are the same number. We're using the identity property of equality that says if I multiply by 1, or a form of 1, then what I get is going to be equivalent to what I started with. Okay, now I can add these together to get my final fraction. Okay, now we're not adding fractions here in this assignment, but the point that I was trying to make is this idea of using the identity property of multiplication allows us to change the denominator. Right? Notice that I changed this denominator from 3 to 15, and I changed this denominator from 5 to 15. So I can use the identity property of multiplication to change a denominator, and that's exactly what I want to do here. I want to change this denominator so it doesn't have a root in it. Okay, so I need to multiply it by something that will get rid of that root. So here's the deal. If I multiply the square root of 3 by the square root of 3, then I can get rid of that root. Now, I'll show you how that works in a second. In order to make sure that that happens the right way, or in order to make sure that we're making this like legal, basically, we need to multiply by a form of 1. So just like over here, we had 5/5 and 3/3. Square root of 3 over square root of 3 is just 1. So we're not going to change this fraction. We're just going to change what it looks like. We're not going to change the value. So if I do 1 times 3, 1 times the square root of 3, that's the square root of 3. Okay, but here I have the square root of 3 times the square root of 3. There's a couple different ways we can write this, but one of the ways we could write this is to say, look, if you're multiplying two things with the same root, then you can put those things both inside the root, right? So this is the square root of 3 times 3, right? Or in other words, the square root of 3 squared, okay? Now that we have a square, the square root and the squared are inverse operations and they're going to undo each other. That's why I multiplied by the square root of 3. I knew that if this is a square root, I need 2 copies of 3 inside in order to take a square root. I need something squared. So this is going to simplify to square root of 3 over, now this guy right here, the square root of 3 squared is just 3, just a regular 3. The square and the square root undo each other. Okay? All right, now, one thing that's really helpful with rationalizing denominators is to use the rational exponent property. Let me show you how that would work. Now, this is perfectly valid, and you don't have to do it twice, but if you want another method, this is another way you could do it. If I rewrite this expression with rational exponents, I get 1 over 3 to the 1/2. Now, my goal here is to make sure that I don't have anything that has a rational exponent in the denominator. So when I write it like this, I know I need to get a whole number exponent, which means I need to multiply by 3 to the 1/2. Okay, so 3 to the 1/2 times 3 to the 1/2, the 1/2 and 1/2 will add to give me a 1, which is what I want. Now I have to do the same thing on top and bottom because I have to use the identity property. I have to multiply by a form of 1. So this will give me 3 to the 1/2 power over 3 to the 1 power, right? Because 1/2 plus 1/2 is 1. When I'm multiplying two things with the same base, I add the exponents. Okay, now I just transfer it back into radical form. So 3 to the 1/2 we know is the square root of 3, and this is a regular 3. So notice either way, I'm going to get the square root of 3 over 3. Okay. In this case, similar kind of idea, right? Notice I have a square root of 7 down there. So what I'm going to want to multiply by is something that gets rid of that root. Okay, and again, there's two ways to do it. Either one of these methods will work. So you can multiply by the square root of 7 over the square root of 7. Okay, or you can come back here and change it into rational exponent form. Okay, from here, it's clear that I need to multiply by a 7 and 1/2 because we want to add these exponents to get a whole number. But if I multiply by 7 to the 1/2 on the bottom, I better multiply by 7 to the 1/2 on the top. Okay, so either way, we're going to get rid of these, this square root of 7. Now I'll let you finish that up using the same kind of idea, but that's where you want to start. All right, as we get more complicated here, there's a couple different strategies that we can use. So in this case, number 11, notice that root 20 is not simplified yet, and we probably want to do that first. In some of these, we have common factors. So in 14, for example, I have an 11 and a 66, and those have a common factor of 11. So I might want to simplify that first. Let's look at 11 and 14 separately, and then we can kind of see how we can use some different techniques here. In this scenario, the first thing I would do is simplify that root 20. If we prime factor 20, we can prime factor that to, or we factor that to 5 and 4. 5's prime. And then 4 is 2 and 2. Right. So what this is going to turn into is 12 root 3 over the square root of 5 to the 1, 2 to the 2. Now notice that I have a 2 squared inside of a square root. So already this square root, this 2 root, and this 2 power should undo each other. So when I rewrite this, the square root of 2 squared, I can take the square root of 2 squared. It's just 2. Now the square root of 5 to the 1 I can't do yet, so I have to leave that alone for now. So that's where we're at. Okay, so I have a 12 over 2, which we can simplify. Let's save that to the end. We could do it now if we wanted to. But let's focus on this guy right here. Okay, I want to get rid of that square root. And I can only take the square root of things that are squared. So what I need here, this is 5 to the 1, I need a 5 squared. Which means I need to multiply by a root 5 to the 1, root 5 to the 1. In other words, just a root 5, right? Now what's going to happen is I'm going to have a 5 times a 5, which is a 5 squared. Okay, so what if I keep going here? I'm going to have a 12 root 3 times the square root of 5. That's on top. 12 times root 3 times square root of 5. Okay, on the bottom, I have 2 times root of 5 squared. Right, because 5 times 5, they're both under a radical. I can put 5 times 5 under the same radical now. So that square and that square root will undo each other. This is where I'm multiplying by a form of 1. This is the identity property right here. All right, so what we're going to have here is going to be 12 times the square root of 3 times 5. No, I'm going to combine these now. Over 2, and this square root of 5 squared is 5, right? The square root and the square undo each other. That's just 2 times 5. And then the 2 goes into the 12 6 times. And so final answer here is 6 times root 15 over 5. Now I can't simplify the 15 over the 5 because this is in a root and this is not in a root. So this is as simple as I can get it. All right. Now real quick, I want to look at that same problem again with rational exponents because that helps a lot of people to see what's happening here. So let's go back to this stage. Okay, so going back here, I'm just going to use kind of a scratch paper since I ran out of room. Okay, if I write this as 12 root 3 over the square root of 5 to the 1, 2 to the 2, and I rewrite this with rational exponents, you'll see what happens with that 2 and that root canceling. So this will be 12 times 3 to the 1/2 power, right, 'cause square root, over 5 to the 1/2 power. So The power is 1, the root index is 2, so 1 over 2, and then we're going to have 2 over 2 as well. So times 2 to the 2 over 2. Notice that 2 over 2 is 1. It's just a power of 1. So when I write this as rational exponents, you can see that 2 over 2 simplifying. Or in other words, you can see the power of 2 and the root 2 canceling each other out. So I have 12 times 3 to the 1/2 power over 5 to the 1/2 power times 2 to the 1. All right, 2 to the 1. So that's just a regular 2. Now, before in the previous method that I did, I actually waited to cancel this 2, but you don't have to. We could cancel it early, so this is a regular 2 that cancels with a 2 inside there. So I have 6 times 3 root, or 3 to the 1/2 power over 5 to the 1/2. Okay, so let's rewrite that. Okay, now remember our goal is to make sure that there's no roots in the denominator. In other words, everything in the denominator has to have a whole number power. So if I want that to be a whole number power, I need to multiply by 5 to the 1/2 power. I have to do that on top as well, so that I'm actually using my identity property. All right, so this is going to give us 6 times 3 to the 1/2 power times 5 to the 1/2 power. Right, that's the top. 6 times 3 to the 1/2 times 5 to the 1/2. On the bottom, I have 5 to the 1/2 times 5 to the 1/2, which is 5 to the 1. Because when I'm multiplying something with the same bases, I add the exponents. Okay, now these two guys right here, I can't do anything with them. I can't simplify them. They're roots now. So they're root 2, or they're the second root. Excuse me, the index number is 2, square root. And then 3 to the 1, 5 to the 1. So I have 6 times the square root of 3 to the 1 times 5 to the 1 over 5 to the 1. And then finally, 6 root 15, because 3 times 5 is 15, over 5. Right. So the exact same answer that I got before. Okay, this is just using rational exponents to simplify the roots. And some people can see a little bit easier what they need to multiply by here in order to get the bottom to have a whole number exponent. Okay. All right, let's look at 14, which has a little bit different strategy. So in number 11, I had to simplify that root 20, but so I did that off to the side. Now 3 and 20 don't have any common factors, but in 14, I do have some common factors here. So I can rewrite this part as root 11 over 66. Now I still have that 18 multiplying out front, so I'm going to write it like that. Okay, the advantage of that is now I have 18 to the square root of 18 times the square root of 1/6. Okay, rewrite it again. I have 18 times the square root of 1 over the square root of 6. And the square root of 1 is just 1. So I have 18 over square root of 6. Okay? So if I factor the bottom now, I have the square root of 2 to the 1 times 3 to the 1. What I need is 2 to the 2 and 3 to the 2. I want these numbers to be squared so that I can take the square root. Okay, that means I need to multiply by the square root of 2 to the 1 times 3 to the 1. Got to do that on top and on bottom. All right, so I have 18 times the square root of 2 to the 1 times 3 to the 1. That's just going to be 18 times root 6. Nothing's going to simplify here on the top, so I'm just going to do 2 times 3. That's going to be 6. But on the bottom, I have the square root now of 2 squared, 3 squared. Because I have 2 times 2, that's 2 squared, and 3 times 3, that's 3 squared, but all under the same root. Okay, so the square root of 2 squared is 2. This square root here and this 2, this power of 2, undo each other. I just get a regular 2 down there. This square root and this power of 2 also undo each other, so I get a regular 3 down there on the bottom. So I have 18 times root 6 over 2 times 3, which is 6. So 2 times 3, that's 6. goes into 18 3 times. So 6 goes into 18 3 times, and I end up with 3 root 6. Okay. Now you could do this with rational exponents again, if you want to. I'm going to leave that one there, and I'm going to do another one, and the next one I do, I'll use rational exponents. Okay. So on the back page, we have the same kind of idea. We just have higher powers. So on 15 through 20, we need to rationalize these denominators. But we probably need to start by simplifying to see what we have. Okay. Let's take a look at 18 as an example. Okay, now I have the fourth root of 27. But 27 is 9 times 3, and 9 is 3 times 3. So if I rewrite this with 27 factored, I get the fourth root of 3 to the third on the bottom and 15 on the top. Okay, now let's rewrite this with rational exponents. I think that'll be really helpful here. So if I have 15 over this root and I want to rewrite the root, I can rewrite that as 3 to the 3 over 4. Okay. Now if you look at that rational exponent, 3 over 4, I have to think what will complete that rational exponent and make it a whole number. Right? If I have 3 out of the 4, I need just one more. So what I'm going to multiply this by is 3 to the 1/4 power, because 1/4 plus 3/4 is 1. Got to make sure I do that on the top as well. Okay. So one of the things that I wanted to point out is that these two things do not have to match. On the previous page, sometimes they do. But with higher powers, these things aren't necessarily going to match, and that's okay. The powers don't have to match. Now, these have to match, of course, because this needs to be a 1. But we just basically want to figure out the bare minimum that we need to be able to combine these exponents to get a whole number. So on the top, we're going to have 15 times 3 to the 1/4. Okay, remember this power of 15 is just a regular 1. Now on the bottom, we have 3 to the 1 power, right? 3/4 plus 1/4 is just 1. So the 3 here, and there's a 3 in here in the 15, that can cancel. 3 goes into 15 5 times, and I end up with 5 times the fourth root of 3. Okay? You can do something similar on... Well, I mean, all these are kind of similar in this section, but like 16 is kind of similar because we have 3 over the third root of 5 squared. Right, 25 is 5 squared. So when I write this here with rational exponents, I have 3 over 5 to the 2/3. Okay, so think to yourself, what will complete that exponent so that it's a whole number? I need a third. So I'm going to multiply by 5 to the third over 5 to the third. Okay, on the top, I just have 3 times 5 to the 1/3 power, and nothing's really going to happen there. But on the bottom, I now get 5 to the 1 power, right? Because 2/3 plus 1/3 is 1. So on the top, 3 times 5 to the 1/3. Now I'm going to turn this back into root form because I can't do anything left, or there's nothing left to do. So 3 times the third root of 5, right, this is the third root of 5, over 5. Okay. So again, these two things, what I'm multiplying by, they don't have to match. These have to match, but these don't have to match. Don't multiply by anything more than you absolutely need to get the whole number exponent. Okay, let's look at some problems here from the bottom. So this looks a little scary. There's a lot going on here, but we have now all the tools that we need to be able to simplify those guys. So let's take a look at what we have. Right, the first thing we need to do is simplify what's inside the root. So in this first example, I have 3p to the third over 5 times the square root of 2 to the 3 p to the 1. Okay, I rewrote 8 as 2 to the third power, so that's kind of like a prime factor idea. Okay, Now, if you're a root person, you might think to yourself, okay, as long as I get p squared and 2 to the 4th, I can take the square root of that. If you're a rational exponent person, you're just looking for whole number exponents. Okay, so let's rewrite this. 3p to the 3 over 5 times 2 to the 3 halves p to the 1 half. Right? So if you look at these guys here, you got to figure out what's missing. How can I get these guys to be a whole number? So I have a 2 to the 3 halves. It'd be great if I could get that to a 4 halves, because that would be a whole number. And it'd be great if I could get this to be a 2 halves, because that would be a whole number. So what I need in order to rationalize the denominator is I need a 2 to the 1 half and a p to the 1 half. I'm going to need to do that on the top and the bottom. Okay, so again, that's my form. That's my 1, right? Multiplying by 1. And so on the top, I'm going to get 3p to the 3rd. And I'm going to have 2 to the 1 half, and I'm going to have p to the 1 half. So that gets kind of messy on top. Okay, the bottom is where it really cleans up. So I got that 5 that was there. Okay, now I have 2 to the 4 halves, because I have 3 halves plus 1 half. So that's 2 to the 4 halves, or 2 to the 2, because 4 halves is 2, right? 4 over 2 is 2. Okay, and then I have p to the 1. So p to the 1 half times p to the 1 half. The 1 half and the 1 half add, and I get p to the 1. Okay, so changing this back into like root form, I have 3p to the 3rd times the square root of 2p, because 2 to the 1 half and p to the 1 half are just square roots, over 5 times 4, that's 20, and then another p. Now since there's 3 p's up here and 1 p down here, this p can cancel with one of the p's here, and I'm going to have p squared. So it's 3p squared times the square root of 2p over 20. Okay, so use those. I recommend using rational exponents on these, especially when you have, variables and powers and stuff. Okay, let's look at a few more here to help you out. All right, let's take a look at, well, that one has an 8 in it. Let's do 32. Okay, so again, start out by factoring the bottom to see what you have. So I have 8 over the 4th root of 5 squared u to the 3. So 25 we know is 5 squared. Okay, let's write this as rational exponents. So 5 to the 2/4 u to the 3/4. Right, now we could simplify this right now if we wanted to make it 1/2, but we're not going to do that just yet because we want to multiply. We want to multiply by things that have the same denominator, so that our index is the same. So what we need here is we need to complete this, so this is a whole number, and we need to complete this guy so it's a whole number as well. So I need I need to have 5 to the 2/4, because that will give me 4/4, and then I need to have u to the 1/4. Okay, so on top, same thing, 5 to the 2/4 over u to the 1/4. All right, so on top, I get 8 times 5 to the 2/4 times u to the 1/4. So the top doesn't really get that much nicer. On the bottom, though, I now have 5 to the 4/4. Right? 2/4 plus 2/4 is 4/4, or 1. And I have u to the 4/4, because 3/4 plus 1/4 is also 4/4, so u to the 1. All right, so now turn this back into roots here. I have 8. Okay, now the reason why I didn't change this to a 1/2 power here is because I want to put these all in the same root, and I can't really do that if these are not the same number. So if I simplified this to a 1/2 power right now, I would have the square root of 5, and this is going to be the 4th root of u. So that's probably, we're not going to simplify that guy. We're just going to write the 4th root of 5 squared, which is 25, times u. So that's the top. 8 times the 4th root of 5 squared u, or 25u. On the bottom, I have a 5 and a u. Okay, now, again, like we talked about before, because this isn't in a root on the bottom, I can't divide out, because this isn't a root, I can't divide the 5 here or the u here, so this is as far as we can go. Okay, so again, that 5 to the 1, u to the 1, it came from this, adding these fractions right here. All right. Let's take a look at 23. 23 looks a little ugly. Now I'm going to do this on a separate sheet of paper because I'm getting a little cramped over here. But this one has a root in the top. Okay. Now, one of the properties that we talked about is to put everything under the same root. So you might be looking at this and being like, oh, well, some things simplify here, and I can take this x squared out. Probably what I would do in this scenario is write it as one big root and do 2x squared y over 5x squared y. The reason being is now I can cancel the y over the y and the x squared of the x squared. So that makes my life a whole lot easier. Now I have just the square root of 2 over the square root of 5. Okay. If I want to rationalize this, I need to get rid of the root in the bottom. So if I want to do rational exponents, this is 2 to the 1/2 over 5 to the 1/2. So what's going to make that a whole number? It's another 5 to the 1/2 power. All right, so on the bottom, I get 5 to the 1/2 times 5 to the 1/2, which is 5 to the 1. On the top, I get 2 to the 1/2 times 5 to the 1/2. Okay. So when I rewrite this with roots, I'm going to have the square root of 2 times 5 over 5, or the square root of 10 over 5. All right, so that one looks pretty ugly, and you're like, oh man, I got the roots on top and on the bottom. But a lot of this stuff can just cancel out from the get-go. All right. Okay, so that should help you get started. Again, I recommend using rational exponents here as much as possible. I think it's easier to see how to get your numbers to cancel out when you're multiplying. We want to get whole number exponents. So look at those examples, view those examples, use those examples to help you get going on the other problems, and I'll see you guys back in class. Thanks.